Today, I'm presenting the paper MQTTactic Security Analysis and Verification for Logic Flaws in MQTT Implementations towards my course CS6263. This paper was published at the 2024 IEEE Symposium on Security and Privacy. The main focus of this paper is MQTT broker security. MQTT is widely used in Internet of Things and cyber physical systems, but the authors show that broker implementations can contain subtle authorization logic flaws. The paper proposes MQTTactic, a semi-automatic tool that uses static code analysis, formal modeling, and model checking to detect these flaws. Here is the roadmap for my presentation. I will first explain the motivation and MQTT background. Then I will describe the main security problem and the threat model. After that, I will explain the key idea behind MQTTactic, including its architecture, formal model, and a model checking process. Then I will discuss the evaluation results, representative flaws, defenses, limitations, and finally my own critique and conclusion. MQTT is one of the most widely used messaging protocols in Internet of Things systems. It connects users, applications, cloud services, and IoT devices using a lightweight publish subscribe model. Many commercial Internet of Things platforms and open source systems rely on MQTT brokers to mediate communication. This is important because a security flaw in a broker can affect many downstream systems. So the paper's motivation is that MQTT brokers are not just small software components. They are security critical middleware in modern Internet of Things and cyber physical systems environments. This topic this topic is highly relevant to cyber physical systems and industrial control systems. MQTT can be used in smart homes, IoT gateways, edge systems, and cloud connected monitoring applications. In CPS and ICS, the messages may represent sensor data, status updates, or even control commands. If an attacker can exploit MQTT authorization logic, the impact may not be limited to the data leakage. It can affect the integrity of operational commands and potentially influence physical processes. MQTT uses public subscribe communication model. A publisher sends a message to a topic. A subscriber expresses interest in a topic and receives messages through the broker. So the broker is the central component that receives, stores, routes, and delivers messages. The clients do not need to communicate directly with each other. The design is efficient, but it also makes the broker a very important security enforcement point. There are few key MQTT concepts needed to understand from this paper. A client can be a user, device, or application. The broker is the server side implementation that manages communication. A topic is like a logical channel or a message category. Publish is used to send messages and subscribe is used to receive messages. MQTT also supports different quality of service levels, which affect how messages are delivered. These features create complex broker logic, and that complexity is where many authorization mistakes can occur. Now I'm moving into the main problem. The core issue is that authorization must be complete, timely, and implementation aware. It is not enough to check permission only once. In MQTT, messages can be stored, delayed, retired, or triggered later. So a client may have permission at one point, but lose permission before the message is actually delivered. That creates subtle logic problems. The basic security requirement is simple. Only authorized clients should publish messages and only authorized clients should receive messages. However, the difficult part is enforcing this correctly across all broker logic paths. Permissions can change over time. A user can be authorized first and then revoked later. A secure broker must make sure that revoked users cannot continue to influence message delivery through delayed or cached protocol behavior. This paper explains that the MQTT specification mainly defines messaging behavior. It doesn't fully specify where authorization checks should be placed in every implementation path. As a result, developers often customize broker logic and insert permission checks in different locations. This can lead to missed checks or checks at the wrong time. These are not simple bugs like weak passwords. They are logic flaws caused by the interaction between protocol behavior, implementation choices, and dynamic permissions. Prior work often used dynamic testing or black box analysis. Dynamic testing is useful, but it depends heavily on the test cases that are generated. If a test does not exercise a rare sequence of actions, the flaw may be missed. The authors argue that MQTT authorization flaws require deeper reasoning about broker states and possible action sequences. This is why they use source code guided modeling and a formal model checking instead of relying only on the runtime testing. The threat model assumes that the broker and devices are benign, but users may be malicious. The attacker may be a user who once had a legitimate access but later loses permission. For example, an Airbnb guest may have temporary access to a smart lock, but that access should expire after he checks out. The attacker's goal is to exploit MQTT logic so that messages are still delivered or triggered after authorization is revoked. The main research question is, can we systematically detect authorization related logic flaws in real MQTT broker implementations? This is challenging because different brokers implement MQTT differently. The authors also want to know whether source code can be abstracted into useful formal models and whether model checking can find real flaws in popular open source brokers. Now I will explain the solution proposed in the paper. The tool is called MQTTactic. The key idea is to build broker specific models from source code and then use model checking to verify whether authorization properties always hold instead of creating one generic model for all brokers. MQT tactic extracts implementation specific behavior from each broker. MQT tactic is a semi-automatic tool for analyzing MQTT broker security. It combines static code analysis, formal modeling, and automated model checking. The tool focuses on authorization-related logic flaws. At a high level, MQTtactic takes broker source code, extracts security-relevant behavior, generates a formal model, checks security properties, and reports counter examples when a violation is found. This slide shows the overall MQTtactic architecture. The input is MQTT broker source code and a configuration file. The source code is converted into LLVM intermediate representation. Then the model generator extracts relevant control flows and constructs a model in Promela. Spin is then used as the model checker. If Spin finds violation of the security properties, MQTTactic reports a counterexample, which the authors then validate using proof of concept experiments. One important design decision is that MQTTactic does not use unified one model for all brokers. This is because real MQTT brokers customize the specification in different ways. Permission checks may appear in different functions, and message handling paths may differ across implementations. Therefore, MQTT Tactic generates a concrete model for each broker by extracting implementation specific source code information. The paper models an MQTT broker as a state machine. The model includes variables, operators, states, client actions, transition functions, and security properties. The key idea is that MQTT actions such as connect, publish, subscribe, and publish can change broker state. MQTT tactic checks whether unsafe states are reachable. If an unsafe state is reachable, that means there may be an authorization logic flaw. MQT tactic focuses on security relevant state variables. Examples include subscriptions, related messages, retained messages, message queues, will messages, and permissions. It also models operations such as read, write, add, remove, and deliver. The this abstraction is important because the tool does not need to model every low level detail of the broker. It only needs to model the behavior that affects MQTT security state and authorization decisions. The tool models important MQTT client actions such as connect, publish, publish, subscribe, unsubscribe, and disconnect. It also models authorization related actions such as authorize and revoke. The revoke action is especially important because many flaws occur when permission changes after a message has already been accepted, stored, delayed, or queued. MQT tactic begins from action handler functions in the broker source code. It identifies key basic logs that affect the broker state. If then keeps the relevant control flow paths and removes implementations, the details that do not affect the security model. This paper calls these effective path types. In simple terms, MQT tactic reduces complex source code into a formal model that captures only the security relevant behavior. Once the Promella model is generated, Spin explores different possible sequences of client actions. For example, a client may publish a message, another action may revoke permission, and then the broker may later deliver a stored message. Spin checks whether the required security properties still hold in every reachable state. If property is violated, Spin provides a counter example showing the action sequence that led to the violation. MQT tactic checks three main authorization properties. First, a receiver must have permission to receive a message. Second, a sender must have permission when the broker accepts the message. Third, the client that triggers delivery must still have permission when the message is delivered. The third property is very important because it catches timing related and asynchronous delivery flaws that may not be obvious from normal testing. So now I will move to the results. The key point is that MQT tactic found real authorization logic flaws in real MQTT broker implementations. This shows that approach is not only theoretical, it found practical issues in popular open source brokers, including previously unknown zero-day flaws. The authors evaluated MQTTactic on 7 popular open source MQTT brokers. These brokers were written in languages such as C, C++, Go, and Rust. The focus was on authorization-related logic flaws. After MQTT-Tactic required possible issues, the authors manually validated them using proof of concept experiments in their own lab environment. The main result is significant. MQTT-Tactic found 11 authorization-related logic flaws. 7 of them were zero-day flaws, meaning they were previously unknown. 4 were existing flaws. These flaws showed practical unauthorized access risks. This result supports the paper's claim that MQTT broker authorization logic is difficult to implement correctly and that formal verification can reveal subtle problems. This is one of the most important examples. In QoS2 messaging, a publisher sends a message and the broker stores it before final delivery. The attacker can delay the Perbrel packet, which controls when the broker continues delivery. If the attacker's permission is revoked during this delay, the broker may still deliver the messages later. So the attacker can cause message delivery after losing authorization. This is a timing manipulation flaw. The paper identifies several classes of zero-day flaws. These include delivery retry flaws in QoS1 and QoS2, unguarded use of topic alias, insecure session takeover, unvetted will messages, and vulnerable message caching. The common pattern is that broker performs an authorization check at one point but misses another security critical point later in the messaging lifecycle. So the most direct mitigation is to recheck authorization at every security critical step, especially at a delivery time. Brokers should not rely only on permission checks performed when message is first accepted. Developers also need a clearer security guidance for MQTT implementation. From an OT and a CPS perspective, this should be combined with a defense in depth, network segmentation, broker hardening, logging, monitoring, and controlled communication paths between cloud, DMZ, and OT zones. The paper also has some limitations. MQTTactic currently focuses mainly on authorization related properties. It does not fully cover authentication, secrecy, memory safely, or denial of services issues. It also needs to configure configuration to map actions and variables in each broker. Another limitation is language support because the approach depends on generating LLVMIR. Future work could extend the model to more security properties, more protocols, and more implementation languages. From my perspective, this is a strong paper because it finds subtle logic flaws rather than only obvious configuration mistakes. The formal verification approach provides a stronger confidence than ordinary testing. It is also relevant to IoT supply chain security because open source brokers may refuse it by many vendors. For industrial environments, the paper is a reminder that protocol security must be combined with architecture, monitoring, access control, and operational discipline. To conclude, MQTT brokers are security critical middleware in Internet of Things and cyber physical systems. Authorization flaws can survive even when basic checks are present because MQTT messaging can involve delayed delivery, retry, caching, session takeover, and will messages. MQTTactic builds broker-specific formal models and uses spin model checking to find counterexamples. The authors found 11 logic flaws, including 7 zero days. The key lesson is that MQTT is lightweight, but MQTT security cannot be lightweight. This slide lists the main reference for the presentation, the MQT tactic paper by Bin Yuan and co-authors, published at the IEEE Symposium on Security and Privacy in 2024. I also used paper's architecture and flaw examples to explain the problem, solution, and results. Thank you for listening. I'm happy to take any questions.